This is AP Exam Review, Video 1, over Chapters 1 through 3 of the AP Exam. A quick word right before we begin. There are no calculators allowed on the multiple choice. No calcs, which will make our calculations, which we'll have to still do, very fun. So get ready, and let's go to it. I'm going to just go through a few of these questions, not all of them, and complete the rest on your own. And I would encourage you to really stop and think about each question I am going through, try to solve it yourself, and then you'll get more out of it that way. So we're not going to do the first one. The first one is simply some balancing of equations. Try that one. Number 2, though, let's quickly review the idea of moles and how they're related to atoms. So we have a mole of this compound, potassium zirconium sulfate trihydrate. Now this is a hydrate compound which incorporates water molecules into the compound. So what we've got is we've got K4Zr parentheses SO4 4.3H2O. Remember, each one of these means you have this many moles of that compound, of that element, or that many atoms if you have one molecule of the whole substance. So let's go through it. If we have 1 mole, we have 3 times 6.02 times 10 to the 23rd. Now remember that 1 mole actually is 6.02 times 10 to the 23rd atoms. This is the definition of a mole. So here we have half of a mole of hydrogen atoms. Is that true? Nope, we have 6 moles of hydrogen atoms. So this one's out. Do we have a mole of sulfur atoms? Because this would be 6.02, 10 to the 23 of a mole. Nope, we have actually 4. This 4 corresponds to the sulfur, so this one's out. Do we have 4 moles of potassium atoms? That is correct. Notice we have 4 moles of potassium atoms. This is then the correct answer. The last few 4 moles of oxygen atoms, that's incorrect. We actually have 16 plus another 3, so we have 19. This one's out. And then 4 moles of zirconium. Nope, we actually just have 1 mole of zirconium. So those are out as well. Not bad. How about the next one? We'll actually skip over this one. This requires you to write a little equation. But let's take a look at number 4. If equal masses of the following compounds undergo complete combustion, which will yield the greatest mass of CO2? And the idea here is the mass is always conserved. So the more mass of carbon you begin with, the more mass of CO2 you can get. All the rest of it will come from oxygen. So what we need to find out is which of these compounds has the greatest percentage of carbon. So which percent of carbon is greatest? So if we take a look, really it's the one that's going to have more carbon atoms, relatively speaking. So this one here, C6H6 benzene, actually is the winner. You can circle it, because it has the most carbon as compared to the other elements based on mass. Now remember that percent, to calculate the percent of an element in a compound, you just take the mass of that element, say carbon. In this case, you got 12.01 grams for each carbon, and you got 6 of those, divided by the total mass. So the total mass would be 1201, because you have to account for the carbon, plus 101, because you have to account for the hydrogen. So this actually gives you the highest percentage. You'll multiply by 100 and so forth. This one here has more hydrogens, a little more hydrogen, twice as much hydrogen as this one. So this one has less carbon percent. This one actually has a lot of oxygen, which cuts down on the carbon percent for sure. And this one is 1 to 4 carbon to hydrogen, where this one was 1 to 1. This one was 1 to 2, incidentally. So that's why benzene wins. All right, take a look at the next one here. Let's skip number 5. Try number 5 on your own. Let's do number 6. What number of moles of oxygen is needed to produce 14.2 grams of P4O10 from P? And molecular weight is given to us. What we'll have to do here is actually write the chemical equation. And this is common. You sometimes have to write a chemical equation before you can work with a reaction. So give myself a little more room. And we've got ourselves P4O10 as our product. So P4O10 is our product. That's made from phosphorus and from diatomic oxygen. To balance the equation, you got 4 in front of here and a 5 in front of here. Now, what they'll have you do is do some calculations, some divisions, some multiplications, but the numbers will always be very manageable. They're always going to be, you'll be able to work with it. So notice we have 14.2, and they give you the molar mass. This is common. They give you the molecular weight. So what you could do is you can, to get the moles, remember it's mass divided by molar mass, because you begin with 14.2 grams, and then 1 mole on top, and then grams at the bottom. So you eventually end up dividing 14.2 by 284. Now 14.2 over 284 sounds a little difficult at first, but if it was 14.2 divided by 28.4, wouldn't that just be half? This would be half, correct? 0.5? Now, so because it's not 28.4 but 284, then it becomes 10 times smaller, or 0.05. See if you can follow that logic. This is the sort of stuff you'd have to do when calculating. So here's how many moles of our product, P4O10, we want to make. So 0.05. So if this is 0.05, that means we should have begun with 5 times as much oxygen. So 0.05 times 5 gives you somewhere in the vicinity of 25. So now you can also say, well, which one will give me a 25 number? This one will not, this one will not, and 25 number is right here. But you can also do the calculation like this, and this is another trick I'll show you. If you move the decimal place over twice, in this case, then you end up multiplying 5 by 5. 5 by 5 is 25, and since we've moved the decimal place twice, we have to move it back twice, and that's what we'll do here, giving you 0.25. So that is how you get that answer. All right, let's take a look at number 7, this one here. We got a similar situation. We have an equation. The equation is actually balanced for us. And then we have a mass of the first reactant, N2H4, a mass of the second reactant, and they're mixed together and react according to the equation above. What's the maximum mass of water that can be produced? Now this is a limiting reactants problem, which you'll see, limiting reactants, if that spells reactants. And the idea is, remember, you want to find out how much water each of these can make, and then whoever makes less is going to be the limiting reactant, is the one that's going to be based on. So let me clear, just for clarity's sake, if you take a look, we have 8 grams of this guy. They're giving us the molar mass. So 8 divided by 32, 8 times 4 is 32, so we have a quarter, or 0.25 moles of this reactant, right here. 92 and 92, that makes it easy. We have 1 mole of our second reactant. Now we're going to find out how many moles of water can be made from each. So, because this one, 0.25, it's a 2 to 4 mole ratio, so we make twice as much water. This will actually make 0.5 moles of H2O. So we have half a mole of water can be made from the first reactant. The second reactant we have a mole of, and you can make 4 times as much. It's a 1 to 4 ratio, so you can actually make 4 moles of H2O. Now how much will be made? The lower amount. This is the limiting reactant production. So we will only make the lower amount. Now they don't ask us how many moles of water, they ask us the mass of water. Everybody should know that the molar mass of water is 18.02 grams per mole, which means we have to multiply half by 18, makes it easy, 9 grams. So think through that one. Let's go on to the next one, number 8. Number 8 asks us a percentage yield. So what is the percentage yield of oxygen if 12.3 grams of potassium chlorate, again, molar mass is given, is decomposed to produce this much? Now this is a percent yield problem. Remember, percent yield is how much theoretical you have, or theoretical you should have been produced, versus how much actual. So it's how much did you actually produce versus how much you should have produced. Now the theoretical comes from stoichiometry. And that's how you would do this problem. So we have to find out the actual and then the theoretical. Now the actual is this one right here. So 3.2 grams is actually produced. That's our actual number. And the theoretical will be determined from the original. Remember, you have to convert KCl3 to how much oxygen will be produced first. Now the molar masses, notice, are very easy to work with. So we have 1/10 of a mole. If you divide 12.3 by 123, you get 0.1 mole of KClO3. That's how much you begin with. Now based on the equation, you have to balance it. So if we balance this equation, notice it's not balanced. This is a 2. Nope, that's a 3. That's a 2, and that's a 2. 2 moles of KClO3 produce 3 moles of water. So in order to do this little calculation, let's set up a little bit of a, get rid of this. Let's set up a little bit of a stoich problem. So we have moles of KClO3, and we have 2 moles of KClO3 for 3 moles of O2. So we divide 0.1 by 2. Now we can't use a calculator, so this gives us roughly a 0.05, not roughly, but exactly. 0.05 times 3 gives us 0.15. So 0.15 moles. This is our theoretical. Now the actual is 3.2 grams divided by 32. So actually, that makes it easy. 0.1 moles is our actual. What's left to do is divide 0.1 by 0.15, and then times 100. So 0.1 divided by 0.15 can't be 100% because that would make these match. It's not 50% because half of 15 is 7.5, and it's not 33% because it would be less. So this is actually 67%. So you can actually guesstimate. After you got this number, you can probably guesstimate. All right, let's go to a problem on the back, or 2. So notice I'm flying pretty quickly. If you take a look, number 13 is a quick problem over, let's see, I'm actually going to skip 13. All right, let's finish the video here, and I will put another video up for a few more multiple choice questions. All right.